So today I'm going to talk about caching, and I'm going to proceed in three parts. So first, I'm going to do a little bit of why we should care about caching at all and why we need a new caching solution. Caching is probably something we learned about in our first computer science textbook when we were first getting started, and we know there are a lot of other caching solutions out there. So why is this something that we need to be talking about at all? Then once we kind of establish what the problem is, we're going to talk a little bit about what would an ideal caching solution for the ZIO ecosystem look like. And that's going to lead us into talking about ZIO Cache, which is a new ZIO library that provides that kind of caching solution. And spoiler alert, it's going to look a lot similar to what we said that ideal solution would look like. So with that, let's dive in a little bit. So how did I get interested in caching? Well, as Sandra mentioned, I am the author of a library called ZIO Query, which does query optimization. And so it'll do pipelining, batching, and caching of queries. So if you have some big query you're doing, where as part of it you're saying, get information on all my users, and then as some other part of it you're saying, well, get information on users Dave, Bob, and Carol, it's going to be smart enough to make sure that you don't request that data twice from the underlying data source that you're working with. And one of the things it's going to do there to facilitate that is it's going to cache those requests so that if you got that information on Dave and Bob and Carol as part of that first request, it's going to be available to all other parts of that bigger query that you're creating. And so as part of providing that caching, you actually need to have a cache to do that. And so initially when I wrote ZIO Query, I created my own minimal implementation of a cache, but that got me thinking about what would the right ideal representation for a cache working with ZIO and with the power we have from that look like, and how could that be fit in a more compositional way, where instead of just ZIO Query saying, well, we've just got our own cache data type, we have some more general concept of a cache that you can use with this, that you can use with other things, and that all fits together nicely with everything else that you're doing. So what are the benefits of caching? Why is this important? Well, the way I think about it, there are really two benefits. So one is compositionality and the other is performance. And I think compositionality in a way often becomes the less appreciated one. And that's really what a lot of the motivation for ZIO Query is. Because if we want our applications to be compositional, then we want to be able to build each part of our application separately. So you can imagine if we're working on some social networking site, we might have one part of our application that's supposed to render all of the users' friends and tell them what their friends are doing. And then we might have another part that's supposed to serve relevant ads to users. And it might be that both of those parts, we want to get data on who the user's friends are and what they are doing or what they're buying, so that we can both serve the most relevant ads and tell you about what your friends are doing. And so we might both be kind of querying that same underlying data source. And there's an inefficiency there that we want to avoid. And so we could just try to refactor that and kind of push all that up to another level where we say, okay, well, first we're going to get all this data, and then we're going to push it to these different parts of our application. But that makes our application less modular, where all these different, potentially different teams that are working on these different parts of the application have to know about these different things, and we have to kind of re-architect for that. Versus if we know that we're going to cache these requests, then each part of these applications can be written separately, can pull whatever data it needs, and we can rely on having a cache to say we're not going to end up doing duplicate work there. The other obvious benefit of caching is performance. So before we're talking more about the client side of caching, of we're writing an application, we're making all these requests, and we want to make sure we don't want to make duplicate requests. The other side of it is if we're the provider of this data, then we may receive requests either from the same client or different clients we're working with for information that's the same or overlapping. We may get a ton of different requests for information on Taylor Swift's webpage. And we can be a lot more performant if we say, okay, well, we're just going to put that aside and we're going to serve that to everyone versus re-grabbing that from the underlying data each time. So caching ends up being this really pervasive thing that for lots of applications, we want to have a solution here. And the problem is there's actually not a great caching solution today for the ZIO ecosystem. So there's no ZIO native solution for caching at all. The solutions that are out there often have limited support for asynchronous code. So we'll see that often there's a completely different interface for a synchronous cache versus an asynchronous cache. And that sometimes what an asynchronous cache is actually doesn't give us everything that we want. And there are also a lot of times restricted options for the caching policies that we can have. So typically a cache can only have a certain maximum size. We have to prioritize what things can go in a cache. And often the way that we can do that ends up being pretty hard coded, where maybe we can do it by size, maybe we can do it by age. Those definitely end up being important things, but we don't have a lot of flexibility if we want to really build something more complex and custom a lot of times. So to motivate that, I just put together this simple example here. And so this is just a ZIO effect that's just going to, it's going to print start, just so we know it's starting executing. It's going to sleep for 5 seconds. Then it's going to print a message that's done, so we know those 5 seconds are done. And then it's just going to succeed here with this simple string. So it's just going to have the key, and we're just going to say value here. And what we're going to imagine doing is we're going to call this effect twice in parallel, and then we're just going to print the results. And so this example is obviously a little bit trivial, but what I want you to imagine here is that this computation is being called potentially in 2 very different parts of our program at the same time. Maybe this is in one segment of our application, this is in another segment of our application that's running at the same time, that maybe this is being called 5 levels down in that application. So it's not at all obvious that these things are happening at the same time, but at the same time they're doing the exact same computation. It's an expensive computation, and we only want to do it once. So how can we implement caching so that we ensure that this effect is only going to be evaluated once and its result is going to be available to both parts of our program? Well, so here's one implementation with ScalaCache. And so here we're implementing this memoize method that's going to take a key and a function that, given that key, is going to return a ZIO effect with the value. And we immediately run into a little bit of a problem here that ScalaCache doesn't know anything about ZIO. The best that ScalaCache knows about is future. And so here we're calling this caching F function, which essentially turns a function into something that is going to cache its results with the future. And so we have to get the ZIO runtime, and we have to unsafely run our ZIO effect to a future so that we can fit it into this caching F function. And then this is going to give us back a future that's eventually going to have the result of this computation. And so then we've got to use this other ZIO from future constructor and put this back into a ZIO effect. And because a future can fail for any throwable, we've now got to specialize this to throwable instead of being able to be fully polymorphic in the error type here. And so if we do that, then we can say, okay, we're going to memoize with this key, the effect, and then we'll in parallel memoize again with the key and the effect. The funny thing about this is actually still not going to work, because this caching F is only going to add the key to the cache after the value's been computed. So if these two things are kicked off in parallel, we're still going to compute this twice actually And then when one of them is done, we'll add that key to the value of the cache versus adding the key immediately and having the second just wait for the result. So we can do better here if we go back to the underlying Caffeine cache here, which this is a great caching solution from Java, been around for a long time, very battle tested. But it's a Java API. And so this shows a little bit that here we're going to create this async loading cache, and we're going to feed it this function, that same effect function. And this time, this is expecting a Java feature. So we've got to use this other operator to turn this into a completable feature, and then unsafely run this. And then when we want to implement our own lookup function, we need to turn that Java completable feature back into a ZIO effect. So again, we have that issue of we've lost the type information on the error type. But the good thing is now we can do this, and now this is going to work the way it's supposed to, where as soon as we call this lookup function, the key is going to be added to the cache, and then the subsequent lookup is going to just get that same feature. So this is going to ensure this value is only computed a single time. So to summarize, what are we missing here? Well, we had to unsafely run our effects to a future, and so we lost a lot of the power of ZIO around features like interruption. We lost type information about the way that these effects could fail because we just went back to having things be throwable. In the ScalaCache case, we actually had an issue of not really getting the behavior we wanted under concurrency because of when the key got added to the cache. Now, we can definitely do this ourselves. We've got all the tools in ZIO to handle this. And in fact, in ZIO core, there's a very simplified version of a memoize function that will memoize a particular either effect or effectual function. And we can kind of think about, okay, we could have like a ref that's going to contain a map from keys to promises that are either going to have an error or the value type. And we can kind of manage ourselves every time someone makes a request, we'll modify this ref. And if the key is in there, then we'll return the promise and you can wait on that. And if the key's not in there, then we'll create a new promise and we'll kick off some effect that's going to complete the promise. And we can do all that stuff. But just in doing that, there's like a decent amount of things that we need to make sure we get right. We need to make sure we remove the promises at the right time and handle failures the right way and all this stuff. And we're also not getting any of the other things that we'd like to get from a cache in terms of we'd like to have expiration policies, we'd like to have metrics about what's going on with this cache. We'd like to have some benchmarks on how performant this cache is. And all of this is something where we're having to do a lot ourselves for something that should really be a pretty basic thing that's kind of a off-the-shelf thing that we like just drop in and that solves it for us. So what would it look like if we had a solution that was a real ZIO native caching solution? Well, so if we go back to Caffeine, they had this idea of this loading cache, and that actually ends up being pretty sensible, where we have this trait cache that's parameterized on a key type that we're going to look up, an error that cache computation can fail with, or a value. And its defining method is going to be this get method that just says, give me a key, and I can either fail, or I'm going to return you a value. And that's either an existing value, or if it's not in there, then I'm going to compute it for you. And then we can create a cache by just specifying a capacity for the cache, a lookup function, and we're going to talk about in one sec what that is, and a caching policy. We're also going to talk about what that is. So what does this get us? Well, so with that lookup function, So lookup function is essentially just a function from that key to an effect that's going to return the value. And so the behavior is going to be if the value already exists in the cache, we're just going to return that value. If it doesn't, we're going to compute its value using that lookup function that's inside the cache, and we're going to return it. And what this lets us do is unify those synchronous and asynchronous APIs for a cache. Because one of the nice things about a ZIO effect is it can represent something that's either available right now, that's just ZIO succeed with the number 42, or it can represent some asynchronous computation that's going to return 5 minutes from now after doing a network call and a bunch of work on some remote database. And we can represent that all with that same signature. So we don't need different kinds of caches for synchronous versus asynchronous APIs. We also get the guarantee that a key is going to be immediately added to the cache atomically whenever we call get on the cache. And so even if we have concurrent requests to the cache, we're going to make sure that the cache actually only runs that lookup function once for each of those get calls that comes into the cache. And then subsequent ones are going to suspend until the result from that first call becomes available. So we talked about the lookup function. We talked about the signature of the cache and some of the things it gives us. The other thing that we saw before was this idea of a caching policy. And that's where we get to the idea of being able to be much more extensible and customizable in how we decide what entries are going to stay in the cache. And so a caching policy has two parts. It has what we call a priority and an evict. So the priority you can think of as a policy that deals with optional removal. So it says when we need space in the cache, when we're running out of space, what order can we remove existing values to make more space? And then the evict is about mandatory removal. So it says, regardless of space, when do we need to just kick a value out of the cache because it's no longer valid anymore, because it doesn't satisfy business requirements. Maybe it's too old, for example. And these two things together define a whole caching policy. So this first one, a priority, is really just an ordering specialized for cache entries, right? If you look at the signature of a compare function, this is exactly the signature of a ordering in Scala from the standard library, except we've specialized it to this entry of values, and we've given it contravariance here. And this entry is going to keep track of both a value as well as various statistics about the entry. So the last time it was accessed, how many times it's been accessed, how many times it's been loaded. And so this gives us the ability to prioritize entries in the cache, both by anything about those specific types of values, right? We might say there are certain values, maybe these values are either successes or failures, and we want to make sure we keep the successes, but we're not so interested in keeping the failures. It also lets us prioritize by those other statistics about the entry. So when it was last accessed. The second part of the caching policy is that evict. And this is really just a function from an entry in the current time to a Boolean that says whether that value is valid or not. And so this lets us implement policies that say something like, we don't want to keep any entries in the cache that are more than an hour old, because maybe our service level agreement says we just can't do that. At that point, we need to go, we need to recalculate those values. And together, these two things form a total ordering on cache values. So conceptually, you can think of a valid entry based on that eviction policy is worth more than an invalid one. And otherwise, if we've got two entries that are valid or two entries that are invalid, then the one that has a higher priority is worth more. So it's like ordering by evict and then ordering by priority. And that gives us a really principled and intuitive way to combine these caching policies. And so, for example, we can start to define much more complicated caching policies out of much simpler ones. So here we're first defining an eviction policy that says, here we're saying if an entry is more than an hour old and it's greater than 10 megabytes in size, then we've got to kick it out. And then we're creating an entire caching policy by prioritizing first by last access. So we want to keep the entries that have been accessed most recently. If two entries happen to have been accessed at the same time, let's keep the larger one. And then let's make sure we kick out any entry that's older than an hour and larger than 10 megabytes. And we can combine each of these with this plus plus, and they combine in that very logical way of we're going to order by this and then order by that. And our eviction policy is always going to take priority. So that's an overview of what a ideal solution would look like. Let's go back to our original example and see what would that look like in practice. So here's the same thing with ZIO Cache. So we're just going to create a cache, 10,000 entries. Here we're just going to prioritize by when entries were last accessed. And we're going to give it that same effect we saw before. And then when we in parallel try to do two different calls to the cache, the same key, that's all we have to do. This is going to make sure that that effect computation is only computed once, its value is available in both places, and then we're just going to print the result. And you can see this is like, this snippet is like way shorter than the snippets we saw before. We didn't lose any type information here. So in this case, we can statically know that this fails with an error type of nothing, versus before we had to go back to throwable when we did this. And it's very idiomatic, right? We just did this in one for comprehension. And this will also fit nicely with if we want to make this cache part of the environment, so it's easy to pass around to different parts of our application, we can do that. So what are the key features we get here? We get that ZIO native caching solution. We get a unification of synchronous and asynchronous APIs. We get composable caching policies. And we get cache statistics. So along with being able to just call that get method on the cache and other logical methods like removing keys and things like that, we can also call a method to get the statistics on the cache. And when we do, we get all sorts of things. We get entries, we can get the memory size, we can get hits, misses, loads, evictions, total time spent loading these entries. And so we can actually look at how our cache is doing, and we can decide, well, do we want to modify something about our caching policy to try to improve these metrics? So we're going to be opening this for external contributions after this conference. We're excited to get people starting to use this library and getting your feedback. We're going to be doing much more work on performance. I think the story here is going to be a little bit like the story with ZIO itself, where if you're doing super, super low level things, if you're computing 100 Fibonacci numbers, then sure, you're going to be better using something else. And in reality, you're going to be better just using a map for that. But if you're doing anything that's effectful, where you're doing real IO type work with the things you want to memoize, this is going to be very performant for you. And you're going to get a lot of really nice features, like we talked about, with being able to fit nicely in with everything else you're doing, with being able to compose these caching policies, and it's going to be a really nice solution. So we're excited to get feedback on it and get it out there. In conclusion, I think lessons from this is, in a way, part of this talk was about caching, part of this was just about the power of ZIO. And so some points I'd kind of emphasize to think about is the way that ZIO allows you to unify across synchronous and asynchronous APIs. The benefit of avoiding unnecessary translation between different effect systems, or in this case, it was kind of quasi-effect systems, but whenever we go back and forth between ZIO and future, or ZIO and Java futures, or ZIO and some other effect system that doesn't have typed errors, we end up doing additional work and a lot of times losing information. So if we can avoid that, there's a lot of benefit to doing that. Obviously, sometimes we need to, and that's fine. And then finally, the benefit of composability. Being able to build those caching policies from eviction policies and prioritization policies, and being able to put those together and having that be a very principled thing that, like, I can actually talk to you about, like, the data structure and kind of the thing from, like, category theory, if we ever want to do that, that embodies, even though you don't need to know any of that stuff to use this library, there's a lot of power to that. So to finish off, I want to thank John for his leadership on this project. This was really his brainchild. I want to thank everyone else who contributed to this. I really want to thank Sandra for all of her work in organizing this conference. She's done a ton of work on this that is probably more than any of us can really appreciate, but we're all benefiting from being able to be together this way. All of our sponsors who made this possible. And then finally, all of you for attending today.